statistics that are presented in this video will be exclusively associated with bias factors. This term, bias factor, as introduced by Abu Farsakh et al. In 2010, is defined as the ratio of the measured resistance to the predicted resistance. As discussed in the previous videos related to the AHTD TRC-1204 project, the measured resistance values that were obtained for the TRC-1204 project were collected via Osterberg or O-cell bidirectional load tests. As shown here, the upward and downward movements of the top and bottom plates of the O-cell were plotted as a function of the nominal axial load that was applied to the O-cell from the hydraulic pump. Mutual amounts of movement in the upward and downward directions were then selected, 0.10 centimeters in this example, and the respective upward and downward measured loads at this amount of movement were added together to determine equivalent top-down load. This process was then repeated at various amounts of movement, for example 0.26 centimeters and 0.83 centimeters as shown here, and the top-down curve was developed. This top-down curve should also take into account the elastic compression of the drilled shaft foundation and the weight of the foundation above the O-cell. Sometimes a plunging failure is not observed during the O-cell test. If a plunging failure does not occur, then the movement load curve should be extrapolated by means of a log normal decay function. After application of the log normal decay function, the maximum mobilized axial capacity, defined as the amount of load at a movement value equal to 5% of the diameter of the shaft, can be obtained. From the results of the O-cell test on the south 1.2 meter diameter drilled shaft foundation at the Turl, Arkansas test site, the maximum mobilized axial capacity was 10.97 meganewtons. The denominator of the bias factor is the predicted capacity. Using the geotechnical software packages and the geotechnical engineering parameters that were described in the previous videos related to the AHTD TRC-1204 project, predicted capacities of 5.86 meganewtons, 8.57 meganewtons, 8.60 meganewtons, 6.86 meganewtons, 8.12 meganewtons, and 9.15 meganewtons were obtained when the data from the AHTD, MoDOT, and U of A geotechnical investigation methods were utilized within the FBD and SHAFT software programs. When these predicted resistance values were combined with the measured resistance value of 10.97 meganewtons, as obtained from the elastic compression corrected, extrapolated, measured curve, bias factors of 1.874, 1.281, 1.277, 1.601, 1.352, and 1.200 were obtained. From these different values of bias factors, it's apparent that there was an uncertainty between the measured capacity and the predicted capacity, depending upon which geotechnical investigation technique and which geotechnical software program were utilized. The statistics associated with the TRC-1204 project will now be presented to show how localized and regionalized resistance factors were developed for drilled shaft foundations within the state of Arkansas. Through these statistical processes, a methodology will be introduced to enable a designer to account for the amount of uncertainty in an effort to better design a drilled shaft within the state of Arkansas, in terms of reduced cost for an acceptable level of risk. Moreover, a technique is presented for developing resistance factors when the results from only a small number of load tests are available. Examples will also be presented for clarification. The mean value of the sampled bias factors can be determined by summing the values of the individual bias factors and then dividing by the number of samples that were used. Likewise, the variance value of the sample data can be obtained by dividing the sum of the squares of the differences of the mean bias factors and the individual bias factors by one less than the number of samples that were used. As is common in all statistical processes, the coefficient of variation is defined as the ratio of the standard deviation to the mean bias factor. It is important to note that variance and standard deviation will both be discussed in this video. Therefore, please keep in mind that the standard deviation is obtained by taking the square root of the variance, or the variance is obtained by squaring the standard deviation. A lot of naturally occurring processes, like soil deposits, are often modeled using log normal distribution parameters instead of the normal distribution parameters that were just mentioned. Log normal distribution parameters can either be obtained by 1. Transforming from the normal distribution parameters by using the coefficient of variation value to obtain the expected value for the variance, and then using the expected value of the variance and the mean of the normal distribution to determine the expected value of the mean, or by 2, taking the natural logarithm of the data and then determining the mean and variance using the same principles that were previously described for the normal distribution parameters. If the sample size is limited and not statistically significant, the n-sigma method may be applied to determine the variance of the data. As originally described in Tippett 1925 and utilized in Park et al. 2012, the variance of the limited data is approximated by subtracting the minimum value of the sampled bias factors from the maximum value of the sampled bias factors, and then dividing by a constant that depends on the number of samples utilized. For the TRC 1204 research project, the sample size was either 3 or 6 samples for the localized or regionalized condition, respectively. The corresponding n-sigma values for these respective sample sizes are 1.6926 for 3 samples and 2.5344 for 6 samples. Either normal or log-normal values of bias factor can be used in the n-sigma equation. Bayesian updating is a technique that is commonly utilized to make inference of a given limited dataset by utilizing a larger dataset. For the case of the TRC 1204 project, the larger dataset came from 2 different sources. These sources were a national dataset that was published by Paikowski in 2004 and a regional dataset that was published by Abu Farsak et al. In 2010. The national dataset should be modeled as being normally distributed, but the regional dataset can be modeled as being normally or log-normally distributed. The assumption that the likelihood of the distribution matched the prior distribution was implemented for this project. Then a choice was required. The choice of assuming the variance as being known and being determined by updating the previously described variance using the n-sigma method, or as being unknown and determined using the normal gamma distribution. Because the arithmetic associated with Bayesian updating is much simpler if the data are normally distributed rather than log-normally distributed, the values obtained by taking the natural logarithm of the data were fit using normal distribution parameters rather than being determined through transformations from the log-normal distribution to the expected normal distribution. The posterior mean and posterior variance were then determined by using the mean and variance values of the prior distribution as obtained from Paikowski 2004 or Abu Farsak et al. 2010, along with the mean and variance of the sampled TRC 1204 obtained data. The predictive mean and predictive variance values were then determined by setting the predictive mean equal to the posterior mean and by increasing the posterior variance by the sampled variance respectively. If the sampled variance was considered to be unknown, then the posterior mean was determined by weighting the sampled data by the Paikowski 2004 or Abu Farsak et al. 2010 data. This weighting was accomplished through an equivalent number of samples that either accounted for the ratio of the variance between the sampled data and the Paikowski or Abu Farsak data, as shown here, or by the number of samples in the Paikowski or Abu Farsak dataset. The Paikowski 2004 dataset had 44 samples, while the Abu Farsak et al. 2010 dataset had 22 samples. After the posterior distribution parameters were obtained, Markov chain Monte Carlo sampling was required to determine the posterior distribution and the predictive distribution. All of the predictive parameters were converted from normal distributions to log-normal distributions by using the transformation functions that are shown here. These transformations were required because the live load and dead load combinations were log-normally distributed. After the predicted parameters were transformed, Monte Carlo simulations were performed for the bias factors, the live load, and the dead load. A resistance factor value and a reliability index were then selected, and the limit state function was evaluated for each randomly generated set of values. As shown here, the limit state function included the contribution from the resistance factor, the live load and dead load factors, randomly obtained values of the live load and dead load from Monte Carlo sampling, the log-normally distributed resistance bias factor, and the log-normally distributed load bias factor. For completeness, the values that were utilized in the aforementioned limit state equation are shown here. The number of times that the limit state function was less than 0 was counted, and the probability of failure was determined by dividing the number of times the limit state function was less than 0 by the total number of samples. The reliability index was then calculated by multiplying the cumulative distribution function of the normal distribution of the probability of failure by the probability of failure. If the calculated reliability index was equal to the previously selected reliability index, then the value that was selected for the resistance factor was the appropriate resistance factor. If the calculated reliability index was not equal to the previously selected reliability index, then a new resistance factor was selected and the Monte Carlo procedure was repeated until the calculated value of reliability index matched the selected value of reliability index. Examples of how resistance factors were calculated will now be presented in an effort to help the TRC 1204 subcommittee fully understand the procedures that were utilized. A total of 8 cases will be presented. These are just a few of the cases that were evaluated for the TRC 1204 project. The documentation and results from the other cases are presented in the final report. All of the examples that are provided herein are for the Turl, Arkansas test site using geotechnical data from the U of A geotechnical investigation method and the FBDeep computer model to predict the capacity of the drilled shaft foundations. The considered failure criteria at which the bias factor values were calculated was 5% of the diameter of the drilled shafts, equal to 6.1 centimeters or 9.1 centimeters for the 1.2 meter diameter and 1.6 meter diameter drilled shafts, respectively. Using a method similar to what was presented earlier in this video, bias factor values of 1.01, 1.32, and 1.28 were obtained for the 3 drilled shaft foundations that were tested at the Turl, Arkansas test site. Those drilled shaft foundations being identified as the north 1.2 meter diameter drilled shaft, the center 1.6 meter diameter drilled shaft, and the south 1.2 meter diameter drilled shaft, respectively. Bias factors being larger than unity, the design was considered to be conservative. The first case, identified as case 0A, represented a case in which a normal distribution of normal data was utilized. The n-sigma method and a prior distribution were not utilized when evaluating this case. For this case, the obtained mean value for the bias factor was 1.203, and the obtained amount of variance within the bias factors was 0.029. Moreover, for this case, the mean variance of the sample data and the mean and variance of the posterior distribution were the same respective values. The posterior distribution was then transformed to the log normal distribution, and expected variance and expected mean values of 0.020 and 0.175, respectively, were obtained. The predictive parameters were then input into the open source R statistical software program using this script that is shown here. This script was written to determine the resistance factor through a Monte Carlo simulating process that was described earlier. It is important to note that the standard deviation value, and not the variance value, was used within the R code. It is also important to note that the calculations of the values for the mean and standard deviation of the live load and dead load factors, which are shown in this R code, were previously shown in this video. Using the R code, the resistance factor, or phi value, was then iterated until the beta value was within 0.01 of the required value of 3.00. This led to the probability of failure being approximately 0.001. A resistance factor of 0.881 was obtained by following this methodology. Like case 0A, no n-sigma calculation and no prior distribution were used for case 0B. However, for case 0B, a normal distribution of the natural logarithm of the data was utilized instead of a normal distribution of normal data that was used in case 0A. The values that were obtained from the natural logarithm of the bias factors were 0.008, 0.281, and 0.244, with a value for the natural logarithm of the average bias factor of 0.178. The variance of the natural logarithm of the 3 data values was 0.022, leading to a standard deviation of the natural logarithm of the 3 data values of 0.148. When the mean of the natural logarithm of the data and the standard deviation of the natural logarithm of the data were ingested into the R code, a value for the resistance factor of 0.870 was determined after numerous iterations. The statistical viability of the resistance factors that were determined by using the methods presented in cases 0A and 0B may be questioned due to the limited data set, 3 samples. Therefore, the lack of the number of samples was addressed by using the n-sigma method in cases 1A and 1B. Like with cases 0a and 0b, the normal distribution of the normal data was used in the A case, and the normal distribution of the natural logarithm of the data was used in the B case. Moreover, just like cases 0a and 0b, no prior was used for cases 1a and 1b. For case 1a, the average value of the bias factor was 1.203, and it was the same as the value that was presented in case 0a. But the n sigma obtained variance value of 0.035 was larger than the variance value of 0.029 that was presented in case 0a. Like with case 0a, the respective parameters of the data, the posterior distribution, and the predictive distribution values were all equivalent. When the normal parameters were transformed to predictive parameters, the expected variance and expected mean values of the bias factors were determined to be 0.024 and 0.173 respectively. When the expected mean and expected standard deviations were utilized within the R code, a resistance factor value of 0.853 was obtained after the resistance factor value was iterated until the proper probability of failure value was obtained. For case 1b, the case in which the natural logarithm of the data was considered, the average value of the log normal of the bias factors, 0.178, was the same as that obtained in case 0b, but the n sigma obtained variance value of 0.026 was larger than the 0.022 variance value obtained in case 0b. When the mean and standard deviation values were input into the R code, a resistance factor value of 0.844 was obtained for case 1b. Although several researchers have used the n sigma methods, a more robust approach is suggested by using the Bayesian updating technique. Therefore, the Bayesian updating procedure was utilized for cases 2 through 5. For case 2, the normal distribution of the normal data in the Bayesian 2004 database was used as a prior. For case 3, the normal distribution of the normal data in the Abu-Farsak et al. 2010 database was used as a prior. For case 4, the normal distribution of the natural logarithm of the data in the Abu-Farsak et al. 2010 database was used as a prior. And for case 5, the normal distribution of the normal data in the Bayesian 2004 database was used as a prior. Case 2 was identical to case 1a, except for the addition of the normal distribution of the normal data in the Bayesian database being used as a prior. Likewise, case 3 was identical to case 1a, except for the addition of the normal distribution of the normal data in the Abu-Farsak database being used as a prior. Moreover, case 4 was identical to case 1b, except the addition of the normal distribution of the natural logarithm of the data in the Abu-Farsak database being used as a prior. Finally, case 5 was completely different than any of the other cases because the variance of the variance was also considered using the normal gamma approach. As previously mentioned, the average and variance values for case 2 were the same as for case 1a, 1.203 and 0.035 respectively. The mean and variance values of the posterior distribution of 1.202 and 0.011 respectively were then obtained by weighting the data with the data from a prior distribution. The mean and variance values of 1.19 and 0.13 were obtained from Bayesian 2004. Due to the weighting, the mean and variance values from the predictive parameters of 0.168 and 0.031 were higher and lower than the values of 0.173 and 0.024 that were obtained from case 1a. Likewise, the resulting resistance factor that was obtained, 0.810, was lower than the value that was obtained from case 1a, 0.853. The average and variance values of the data, 1.203 and 0.035 respectively, in case 3 were identical to the values from case 1a. The mean and variance of the posterior distribution parameters of 1.207 and 0.011 were then obtained by weighting the data with the data from the Abu-Farsak prior distribution. Mean and variance values of 1.29 and 0.24 were obtained from the Abu-Farsak et al. 2010 paper. Due to the weighting, the mean and variance values for the predictive parameters of 0.173 and 0.031 were equivalent to and higher than the respective values of 0.173 and 0.024 that were obtained from case 1A. Likewise, the resulting resistance factor that was obtained, 0.809, was lower than the value that was obtained from case 1A, 0.853. The average and variance values of the natural logarithm of the data, 0.178 and 0.026, respectively, in case 4 were identical to the values from case 1B. The mean and variance of the posterior distribution parameters of 0.179 and 0.008 were then obtained by weighting the data with the data from the Abu-Farsak prior distribution. Mean and variance values of 0.19 and 0.12 as obtained from Abu-Farsak et al. 2010. Due to the weighting, the mean and variance values for the predictive parameters of 0.179 and 0.034 were higher than the values of 0.178 and 0.026 that were obtained from case 1B. Likewise, the resulting resistance factor that was obtained, 0.794, was lower than the value that was obtained from case 1A, 0.844. The average and variance values for case 5 were the same as the values from case 1A, 1.203 and 0.035 respectively. Mean and variance values of the posterior distribution of 1.202 and 0.028 were then obtained by weighting the data with data from a prior distribution. Mean and variance values of 1.19 and 0.13 from Bayesian 2004. The mean and variance of the posterior distribution were then utilized along with the alpha and beta parameters, 1.640 and 0.047 respectively, within the R code. Several Markov chain Monte Carlo simulations were then performed to determine the posterior distribution and the predictive distribution. The predictive parameters were then obtained by determining the expected mean and expected variance values from the log-normal transformation. Due to the normal gamma procedure, the mean and variance values for the predictive parameters of 0.160 and 0.049 were lower and higher than the values of 0.173 and 0.024 that were obtained from case 1A. Likewise, the resulting resistance factor that was obtained, 0.707, was lower than the value obtained from case 1A, 0.853. In summary, the statistical approaches that were presented herein included case 0, in which no n-sigma approximation of the variance was utilized, along with no prior distribution being utilized for the Bayesian updating. Case 1, in which the n-sigma approximation of the variance was utilized, but no prior distribution was utilized for the Bayesian updating. Cases 2 through 4, in which an assumed known variance was utilized, that was obtained through the n-sigma approximation of the variance, along with the variance being weighted by a prior distribution, either Bayesian 2004 or Abu-Farsak et al. 2010, and Case 5, in which an assumed unknown variance was utilized and determined through normal gamma Markov chain Monte Carlo simulations. The obtained resistance factors decreased in value as more variance was introduced. Therefore, other researchers that only use the n-sigma approach to determine the resistance factors may be overpredicting the resistance factor, which may lead to a design that is less safe than desired. However, regardless of which case was used, the resistance factors that were obtained were all larger than the AASHTO recommended value of 0.55 when no load test is performed, or 0.70 when a load test is performed. I got it.
Okay. Are you gonna put this on YouTube?
Yeah, she's gonna make it. So far, so good.
You're 15 seconds in. No, I'm kidding. I'm kidding. I'm kidding.
Tomorrow. You gotta help me out. Take your tongue out and then brush it around your teeth.